Here's another inclined plane problem. So we're pulling up a crate along a frictionless incline. So I recognize it to be an inclined plane problem, so I immediately start drawing the inclined plane for a free body diagram, or force diagram. Gravity is always there, of course. Pulling straight down. Normal force is the surface pushing directly away, like so. But this time we have someone pulling upwards here, applying a force. I'll just call that force applied, like so. So there's our start. That's how we typically always start inclined plane problems. Now, along with an inclined plane problem, and this is 22 degrees, we need to investigate the components of the force due to gravity. And the components due to force due to gravity always give us a triangle that looks like this. Here's our actual physical inclined plane with free body diagram. Here's our component triangle. The component triangle, the parallel component is always opposite the angle. Force due to gravity would be the hypotenuse, and if we need it, this one. We'll always need this guy. This guy, not so often. This component, there's coefficient involved. But this one, pretty well always. The parallel component is what we need. Now, the parallel component due to gravity could be placed on here. There's gravity. The parallel component is like this. It's a component of gravity trying to pull that object down the incline. Now, I'm told in the question that this object is accelerating up, so this force must be overpowering that force. So I'm going to go with pretty standard sort of tug-of-war analysis, that the net force is going to be the stronger force minus the weaker force, larger minus smaller. So when I have this, I look at this and say, well, a force applied is what I'm looking for. That's what I'm asked for. So I'll just do some algebra to isolate it, like so. Parallel component. Now, if I can find these two forces, I can easily find that applied force. So let's go about trying to find these two. Which ones we find first doesn't really matter. How about the parallel component here? Parallel component is opposite the angle, of course, it always is, and therefore sine of the angle being opposite over adjacent. There's the opposite. Did I say opposite over adjacent? I meant opposite over hypotenuse. So like that, excuse me. So the parallel component, therefore, is equal to mg sine theta. You almost always need to calculate this when you do an inclined plane. Almost always. If in doubt, when doing an inclined plane problem, solve for that parallel component. 9.81 times sine of the 22 degrees. The parallel component, therefore, so 22 sine times 9.81 equals times 14 kilograms, and I have the value of the parallel component of gravity, 51.448 newtons. There it is. So I've got that part. Now I only need the F net, and I'm on the go here. Oh, well, F net doesn't look too hard to find now, because F net via Newton's second law is equal to m times a. Therefore, F net equals the 14 kilograms times that acceleration of 2 meters per second squared. So we have 28 newtons. So I'll bring these two values up over here. The F net is 28 newtons. Add that to the parallel component of 51.448 newtons. And I'll get the F net, the F applied from this, which is 79.448 newtons. Great. So I think I have the final answer. Let's check sniffing digits. I look back, and 2 sig digs is the way to go in this particular question, so I'll say 79 newtons. So the force applied is 79 newtons, and that's that.